Hi class, in this video I want to talk about probability, and really what I want to talk about is the basics of probability. So when we introduce the concept of probability, I'm going to talk a lot about some definitions and one formula in this lecture, but we're going to do a lot of coin flips and die roll examples here to illustrate probability, at least initially. And just so we're clear, whenever I talk about die rolls, it's always going to be a six-sided die. Okay, I know there's other sides, but we'll just other dice that have more sides, but we're just going to stick with six-sided dice. Okay, so what we're going to do is we're going to introduce some terminology here initially to help us build towards what we call the classical method for computing probabilities. Okay, so first off, we're going to perform in probability something called an experiment. So it's an active process that leads to a single outcome that cannot be predicted with certain results, and it's repeated. So it's a little wordy, so let me just make it here. What I mean by this is it's an active process, single outcome, that has uncertain results. What I mean by uncertain results is, like when you flip a coin, you could get heads or tails, but you don't know for sure. So that's uncertain results, and it's repeatable, meaning you can just pick the coin up and do it again. So what are some examples of experiments? Well, the first one that I had here was the coin flip. I was just talking about here. You can flip a coin. It has uncertain results, but you can immediately repeat it. The second one is a die roll. You roll a die, you can get the outcomes, 1, 2, 3, 4, 5, 6. Uncertain results, but I can immediately redo it again. And then it could be other things too, like drawing a card from a deck of cards. You can draw a card from a deck of cards, maybe get a queen of spades, whatever, and then what you can do is you can put the card back into the deck and immediately draw it again. Okay, so we're going to be performing these experiments, okay, in probability. And then what we want to define next is what's called the sample space. So it's a list of all the possible outcomes from an experiment, and we denote it with the letter S. Okay, so let's find the sample space first. Let's do a coin flip. Well, I'm going to write sample space with this type of S. And you can write it as an HT for the outcomes are heads, tails. You could even write it as head, tail, like this. I'm always going to just do it with H and T. So it's just a list of all the possible outcomes. Okay, so we could also do find the sample space. Let's say for a die roll. So that sample space, which is denoted as S. Well, when you roll a six-sided die, what are the possible outcomes? You could get a 1, a 2, 3, 4, 5, or a 6. Just like that. So we're going to perform an experiment. The sample space tells us the set or list of all the possible outcomes. And what we're going to be interested in is the probability that a specific event occurs. So an event is any subset of the sample space S. It's typically denoted with the letters A, B, C. In my class, I'll always denote it with the letters E or F. So for example, let's talk about the event, we'll call it E, of flipping heads. We would just show this as E is equal to the set of all those possible outcomes. Well, there's only way that could happen is you flip heads. Or going with the die roll, how about the event, we'll call it F, of rolling an even number. Well, that event F, when you roll a six-sided die, the ways you could roll even number would be the numbers 2, 4, or 6 here. Okay, so we're going to perform an experiment. Okay, we're going to then know the sample space, a list of all the possible outcomes, and then we're going to be interested in specifically finding the probability that some event happens. Well, you can see kind of how we're going to do that. Like, for example, if I'm interested in finding the probability that you flip heads, well, there's one way you can do it. But look over here, there's two possible outcomes. So you can see kind of how we're driving towards computing probabilities. All right, so we're going to denote the probability of event occurring as the following. We denote it as P and then in parentheses E, like this. This is not P times E. This is read as the probability of event E. Okay, that's what this P in parentheses means. So like, for example, if I say, what's the probability of flipping heads? You could write it like this. You could write it as probability flip heads. All right, that could be a little wordy. You could just write it as a probability that you get a head. Or sometimes you'll just even see me write it as the probability that you get an H. Okay, what I write inside here, this event, is just what I need to know, so to realize to help me what I'm computing. Like, probability of flip heads, probability I flip heads, probability I flip heads. Whatever you denote in here is fine as long as you know what you're working towards. Similarly here, you could do it as a probability roll even, or you could write it as a probability roll a 2, or roll a 4, or roll a 6, or I can even sometimes write it as probably you get a 2 or a 4 or a 6. Okay, so can you have negative probabilities? Absolutely not. So you can never have the probability of some event happening be like negative 0.2. That just doesn't work. Can you have a probability that's more than 100% chance? No. You can never have the probability of some event be equal to like 1.2. You can't do that. And we're always going to show probabilities as decimals between 0. So if something has a probability of 0, means it never happens. And 1 signifying 100%, 1 meaning that it always happens. Okay, here's some other, just seeing the rules a little bit in more formal notation. So the probability of any event E must be greater than or equal to 0 and less than or equal to 1. So that's kind of just what I had on the previous slide. So if you ever work a problem and you get a negative answer or an answer greater than 1, it just tells you you did the problem wrong. And so this is interesting. The sum of all the probabilities of all outcomes must be equal to 1. So that is, if you have some sample space that's listed like this is the first event that could happen. This is the second, or the N. Like, for example, the sample space is probability flip heads or tails. If you were to take the probability of each individual event in the sample space, so like the probability you flip heads plus the probability you flip tails. All right, it doesn't matter if there's 2 things or n things. If you add up the probability of each individual event, they must always equal 1. Okay, so we'll use what's called the classical method for computing probability, and it's just a very simple formula to follow. All right, so let's see what it is on the next slide here. All right, and we're going to drive this formula with an example. So let's roll a die once. So you're going to roll a 6-sided die. Okay, I'm just going to roll a die like this. And what we're going to be interested in, all right, is finding the probability that you roll an even number. Okay, so we know this is the sample space. This is the list of all the possible outcomes. So there's 6 elements in this set, or 6 outcomes, if that helps to see that way, or 6 possibilities. All right, so we know that the probability, this is what the classical method is, the probability that any event E occurs. In the numerator, it's just always a simple division problem. It's the number of ways this specific event can occur, E, divided by the total number of possibilities, or the total number of possible outcomes. Okay, so then just by this, what is the probability that you will roll an even number? Well, we know there are 3 ways to roll an even number to get the 2, 4, 6. We know, so that's the number of ways that E can occur. And we know the total number of possible outcomes is 6. So this is just 3 divided by 6, or 1/2. Or as a decimal, it's 0.50. So that's it. Just the number of ways whatever event you're interested in can occur, divided by the total number of outcomes. That's it. All right, let's just work some examples so we can kind of see how this is done. All right, so suppose you flip a coin 3 times in a row, okay? And what you're going to do is you're going to record your result. Well, let me show you what an outcome looks like. You could flip heads 3 times in a row. H, 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 H. That's how I would write this. That's how you would get heads 3 times in a row. But you know what? You could flip a tail, then a head, then a tail. That's another outcome. All the way to everything being tail, tail, tail. All right, so this is how I'm going to show the outcomes. Sorry, how I'm going to show the results of the coin flipping it 3 times in a row. All right, is this a probability experiment? 1. Does it have uncertain results? Yes, it sure does. I don't know what I'm going to get when I flip the coin 3 times in a row. Is it repeatable? Yes. Yes, I can flip a coin, 3 times in a row again. So yes, this is a probability experiment. Okay, great. All right, so what is the sample space? So the sample space for this is the list of all the possible outcomes, okay? So you can do, for very small sample spaces, you can do what's called a tree diagram to figure it out. So what a tree diagram works is like this. You start with a dot and you say, okay, what am I going to do first? First thing I'm going to do is flip the first coin, okay, because I'm going to have to flip it 3 times in a row. Well, I could get a head or a tail on my first flip, okay? On my second flip, I'm going to flip the coin again. Well, I could have gotten another head or a tail. But wait a second, maybe I flipped tails first. So then I could get another head or a tail. And then I'm going to go to my third flip. Okay, well, what if I flipped head, head? Well, then I could get another head or a tail. But what if I flipped a head, then a tail? Well, on my third flip, I can still get a head or a tail. And then you can see here what's going on is that this tree here, all right, each branch is all the possible outcomes. So it looks like one outcome is H, 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 head, head, head. One is head, head, tail. Okay, one is head, tail, head. And then one is head, tail, tail. Next, I could get tail, head, head. Tail, head, tail. Or tail, tail, head. And then finally tail, tail, tail. So it looks like there's 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes in this for this experiment here. Okay, so what's probably you flip all heads? All right, well, just using this classical definition here, it's the number of ways I can flip all heads divided by the total number of possible outcomes. So, number of ways to flip all heads divided by the total number of outcomes. All right, well, how many ways can you flip all heads? Well, look into our sample space. H, H, H. That's the only way you can get all heads. So it's 1, and then the total number of outcomes, the total number of elements in the sample space, which is 8 right there. So it's 1 out of 8. What's the probability exactly 2 tails? Okay. Well, you just have to look through here. All right. What goes in the bottom is the total number of outcomes. Well, this is 8. So you have to flip and say, okay, what outcomes have exactly 2 tails? Okay. Looks like this one has 2 tails. This one has 2 tails. And TTH, this has 2 tails. It can't be TTTT because this has exactly 3 tails. So it looks like there's 1, 2, 3 ways to do this, which would be 3 out of 8. Okay, so I hope that was a good initial example. Let's try another one. Getting away from coin flips, let's get into something about die rolls. So it's the casino game craps. Okay. So maybe you've seen, this game of craps before. Like this is from the movie Iron Man, this picture here, and this is what the table game looks like. But really, I won't get into it. But basically what you're doing is you're going to roll 2 die, and you're going to sum the results. Okay? So you're going to roll 2 dice and sum the results. So let me show you what an outcome looks like. One outcome could be you take your first die, you roll a 1 on it, and you roll a 4 on the second. You add these, your outcome is the number 5. Okay? But what's tricky here is, say on the first die you rolled a 4, and on the second die you rolled a 1, you still get a 5. Okay? It's a different outcome, but get the same result. So rolling a 1-4 is different than rolling a 4-1. And then there's all these other different ones. You could roll a 6-3. And that would be the outcome of a 9, because you're rolling 2 dice and summing the results. Okay? So the next question, what I want to do is I want to get a concept of what the sample space looks like. Okay? And when you go to count the number of things in a sample space, there tends to be a multiplying effect. So when you roll a 6-sided die, there's 6 outcomes for the first die, 6 outcomes for the second die, 6 times 6. The sample space here, as you can see next, there's 36 different outcomes for this game. Okay? We're going to show our outcomes as ordered pairs. So you have your first die, and then you have your second die. So like here, this would be the roll 1-1, which would be the outcome of 2, because you're going to sum the die. This one right here, this is the outcome 2-4, which results in the sum 6. All right, notice that the outcome, rolling a 2-4, is different than rolling a 4-2. All right, you're still saying you rolled a 6, but you got there a different way. Okay? So these are all the possible outcomes of this game. Okay, is this a probability experiment? Yes. Again, you have uncertain results. And it's repeatable. All right, what is the sample space for this? I'm not going to redraw everything here, but it's 1-1. 1-2, 1-3, and you would keep going until you got 6-5, 6-6. So there's 36 elements in this set. In this sample space here. All right, so what is the probability that your roll sums to 7? Okay, so just using the classical definition. It's the number of ways to sum to 7 divided by the total number of outcomes. All right, well, we know the denominator. That's 36, okay? So the number of ways you can sum to 7. Okay, well, think about it. You can roll a 1-6. You can roll a 2-5. You can roll a 3-4. Okay? But remember, you can also roll a 6-1. That's a different outcome. Or a 5-2. That's a different outcome. Or a 4-3. That's a different outcome. So it looks like there's 6 ways to do this. And this answer is 1 out of 6. All right, so what's the probability then it sums to 11? Well, again, it's just 36 the total number of outcomes. You have to figure out the number of different ways you can throw 2 dice and sum to 11. Well, there's only 2 ways to do this. You can roll a 5-6 or you can roll a 6-5. So this is 2 out of 36 here, okay, which would simplify, right? What would this be? 1 out of 18 here. So not the best odds. Okay. Let's try this last example here about M&Ms, okay? So suppose a fun-sized bag of M&Ms contains 9 brown candies, 11 yellow candies, 7 red candies, and 4 orange candies, 2 blue candies, and 2 green candies. Suppose a candy is selected at random. So you have this fun size, here's your bag, and it has 9 brown in there, 6 yellow, and keep going a little bit, typo there. 7 red, 4 orange, 2 blue, and 2 green. So what you're going to do is you're going to mix up this bag and then reach in with your hand. Here's a poorly drawn hand. And you're going to pick one at random. All right, what is the probability you get a yellow? All right, and then what is the probability you get a blue? And then let's comment on the likelihood of the candy being yellow versus blue. Well, the first thing you have to do is add up the total number of candies in a bag. Well, if you take 6 plus 4, or excuse me, 9 plus 6 plus 7 plus 4 plus 2 plus 2, you end up getting 30 bags. Okay, so what that means is when you reach into the bag here, the fun size bag, there's 30 possible outcomes. Okay, so what's the probability it's yellow? Well, it's just the number of yellow divided by the total number of outcomes, 0.2. Okay, 6 out of 30, which reduces to 0.2. Piece of cake. What about the probability that it's blue? All right, well, there's 2 blue, 30 bags. 2 divided by 30 gets you 0.067. Or you could simplify that to 1 out of 15 if you wanted, or this to 1 out of 5. So if it helps to see this, right? Probability of yellow for this next question. Okay, probability of yellow is 6 out of 30. Probability of blue is 2 out of 30. To get to take this 2 to become a 6, you have to multiply it by 3 times. What this means is that selecting a yellow is 3 times as likely as selecting a blue bag of M&Ms. All right, class, this was just a real quick introduction to probability. And what we'll do in the follow-up lectures is work harder and harder problems that are a little bit more interesting.